Okay, so in this video what we want to do is cover 2 or 3 examples of actually how to use the equations and how to manipulate them if necessary. Okay, so what we'll do is I'll use a couple of modified problems from out of the back of the chapter. So I won't be using the exact problems, but we'll do some problems that are somewhat similar. So one of the problems out of the back of the chapter has a problem very similar to this. Let's say the velocity of, not av, but of a car decreases from 20 meters per second to 10 meters per second in 2 seconds. Let's make it 5. Let's make it 5 seconds. Find the acceleration. Okay, so this is the problem and what we're given. Okay, so let's pick the problem apart just a little bit. We know that the car is decreasing from 20 meters per second to 10 meters per second. So 20 meters per second is going to be our initial velocity, and 10 meters per second is going to be our final velocity. Okay, and 5 seconds is our time interval, and we want our acceleration. So if we follow the recipe that we'd been talking about before, where we list out all of our givens, so our givens are going to be VI is equal to 20 meters per second, VF is equal to 10 meters per second, time is equal to 5 seconds, and we want to know what the acceleration is. So if we go back to our equation library, which equation should we use? Well, it turns out that the simplest one is just going to be the definition of acceleration. It's already solved for us. We don't have to do any manipulation, and we can start plugging in our values in. So remember that this is VF minus VI all over T. And so this is going to be VF is 10 meters per second minus 20 meters per second divided by 5 seconds, which is going to be 10 meters per second, negative 10 meters per second, divided by 5 seconds, or negative 2.0 meters per second squared. Okay? And the negative sign, right, the negative sign here indicates the object is decelerating, or it's accelerating in the opposite direction of whatever we've defined it to be positive. Now, we haven't really touched on coordinate systems yet, but we definitely will next chapter. So if that concept is just a little bit fuzzy to you, the idea of deceleration or acceleration in the negative direction, hopefully by the end of the next chapter it'll be a little bit more clear for you. All right, but so for the meantime, just don't bother yourself too much with it. All right, all the negative sign means you can think of it as essentially a slowing down. Okay, so there's one example. Now let's do another example where we are given some information, but we might have to do some algebra. Okay, so for instance, let's say that we're given a car starts from a speed of, oh, I don't know, let's say 20 meters per second. And 3 seconds later, at an acceleration of 4 meters per second squared, what is the final speed or the final velocity? Okay, so a car starts from a speed of 20 meters per second, so that's when our driver starts to notice whatever it is that they're doing. They look down at their dashboard, they're going 20 meters per second, so that's going to be our initial velocity. And after 3 seconds of accelerating at 4 meters per second squared, okay, so this is going to be our acceleration, and 3 seconds is our time interval. We want to know what VF is, okay? So we can start with A equals VF minus VI over T, and we need to get VF by itself. And we can do that by multiplying both sides by T. So VF minus VI equals AT, and VF equals AT plus VI. So A, if you recall, right, was 4 meters per second squared times 3 seconds plus an initial velocity of 20 meters per second squared. And here we're going to get 12, and again our seconds are going to cancel out with one of the squareds down there, so we're going to get 12 meters per second plus 20 meters per second, and so this is going to be 32 meters per second. It's going to be our final velocity. Okay. Now let's look at one where we actually have to calculate the distance that an object travels. Okay. So let's actually look at the problem that we did before. Let's look at the first problem that we did. Okay. Or actually, let's look at the second problem. Let's look at the second problem. So we can also ask the question. Let's do part B. Okay. What is the distance? Okay. And so what we can do is, again, we can put all our information to the side here. Our initial velocity was 20 meters per second. Our time interval was 3 seconds. And our acceleration was 4 meters per second squared. And we want to know what our distance is. So remember that distance equals VIT plus 1/2 AT squared. Okay. So this is going to be 20 meters per second times 3 seconds plus 1/2 times 4 meters per second squared times 3 seconds quantity squared. Okay. Now the square just goes over the t. That's very important to remember. Okay. The square just goes over the t. And so let's do the math now. We're going to get 3 times 20, which is 60. And our seconds up top are going to cancel with our seconds on bottom, so we're going to get 60 meters. Now, this one's a little bit tricky. So 3 squared is 9. 9 times 4 is 36. 36 divided by 2 is 18. And do the units come out? So remember, you do whatever the units that you do to the variables. So when I square this 3 seconds squared, I'm going to get 9 square seconds, right? So this is 9 square seconds. So the seconds up top here are going to cancel out with the seconds on bottom there. And I'm just left with meters. So I have 2 units of the same type. They're both distances, and I can add them up. And so I'm going to get 78 meters. Okay? So that's an example on how to use that formula. Now let's do one more where we actually have to do some algebra with this equation. Okay? Let's actually have to do a problem where we've got to do some algebra with that equation so that we can know how to solve an equation of this type or something like it. Okay? So let's say that we have an object starts from rest and it accelerates at 2 meters per second squared, and we want to know how long will it take to cover a distance of 100 meters. Okay? So, again, our object starts from rest, so VI is going to be equal to 0. Our acceleration is going to be 2, and we know that our distance is 100 meters. Okay? So we have VI of 0, an acceleration of 2 meters per second squared, a distance of 100 meters, and we want to know what the time is going to be for this distance to be covered at this acceleration. Okay, so we can start with the equation VI t plus 1/2 AT squared, but when I plug in 0 for VI, 0 times anything is 0, so this equation just reduces down to D equals 1/2 AT squared. Okay, so this is the version that you should use if VI is 0. Alright, but now we need to solve for t. Okay, we need to solve for t, so the first thing to do is multiply both sides by 2 to get rid of the 1/2. And then I can divide both sides by a, and I'm going to get t squared is equal to 2 times d over a, and then t is going to equal the square root of 2d over a. And a mathematician will tell you that you should always have a plus or a minus sign as you take a square root. But in our specific case, we don't need to worry about that because time will always be positive. Okay? So times will always be positive. So if you've done your formula right, there should not be any funny business with the square root. Okay? You shouldn't get a negative square root, nor should you get a negative inside the square root. All right? So now we can just plug in our numbers. So t is going to be equal to the square root of 2 times our distance of 100 meters divided by our acceleration of 2 meters per second squared, and this is just going to be the square root of 100 meters divided by meters per second squared. Now these units might look a little funny, okay? And we can automatically cancel out our meters that are over the meters, but then we're going to be left with 1 over seconds squared. Okay, so before we take the square root, how do these units come out? Right, so this is the same thing as 1 divided by 1 over seconds squared, and that's the same thing as 1 times seconds squared. So I'm going to get 100 square seconds. So when I take the square root of 100, I'm going to get 10, and when I take the square root of seconds squared, I'm just going to get seconds. So to cover a distance of 100 meters, starting from rest and accelerating at a rate of 2 meters per second squared, it will take 10 seconds to cover a distance just a little bit longer than a football field. So that is how to algebraically manipulate some of those equations. So I hope you find these examples useful and helpful, and we will see you next time when we start on Chapter 3. Take care.